Welcome back. My name is Shlomi. In this video, we are going to talk about keys, private key and public key. We are going to generate a Bitcoin address, and we are going to see what is the relationship between them. Before we start, I want to show you a few websites. This is ecdsa.org. When you enter this site for the first time, it might ask you to move your mouse a little bit to generate some sort of randomness. Then, as you can see, it creates some sort of a single wallet. It creates some sort of a paper wallet. We don't really care for this paper wallet. What we do care is over here, wallet details. And you can see that over here we can enter a private key, and it can provide us with all sorts of information about this key. It will be quite useful later on. There is also the Bitcoin wiki over here. You can see I opened the page, technical background of version 1, Bitcoin addresses. It has some sort of an explanation on how to create a Bitcoin address and how to convert a private key into a Bitcoin address. And there is also this little scheme over here on the side. Here. I think this scheme, I really suggest that you will print it out and have it in front of you when you are working. It's very, very convenient. It's very useful and it's very, very convenient, so just print it out and have it in front of you when you are working. Okay, this scheme, as you can see, it shows how to convert from a public key to a Bitcoin address. But before we get a public key, we first need to generate a private key. So let's go back to the technical background. And over here we can see signed data with private key. Let's see what is a private key. Over here. And we can see that in Bitcoin, a private key is usually 256 byte long number. It's a random number. And it's basically 32 bytes. 256 bits is 32 bytes that is represented in hexadecimal. Okay? So let's generate a random 32 bytes long number. Okay, so this is our code. I've already created a new file called keys.py. I am still using the same project we created last time, the My Bitcoin. And I'm going to import a module called OS, import OS. The OS module has a function called urandom, and this function will allow me to receive some information out of the operating system, some sort of randomness that the operating system itself will generate, and it's very useful when I want to deal with a large random number, like 32 bytes. It's quite large. So let's use it. We are going to create a variable called private key, private key. Going to be equal OS urandom and 32. The argument of this function is the number of bytes. In our case, we want 32 bytes. So that's the argument we're going to insert, 32 bytes. We will also convert these random bytes into hexadecimal. We will encode it into hexadecimal because private key should be encoded as hexadecimal, otherwise we cannot really use it. And that's it. This line of code, basically we just created a normal and standard private key. You can use it in the Bitcoin protocol, and that's it. Basically right now we have a private key. So let's just print it out. Print. This is my private key. And let's put a private key. Come on, private key. And that's it. Now let's run it. This number over here, this is a normal and standard, and it is Bitcoin approved private key. And now what we can do, we can actually copy this key, and we can go back to bitcoinaddresses.org over here, and we can insert this private key in this line. Insert this private key. And let's view details. And now you can see it supplies us with a lot of information about this private key, about what type of public key it might have, and what is the Bitcoin address that is associated with this private key. And it's very, very useful that that you have something to compare your results with. So when you're making your first step, you have this some sort of support, this type of debugging. You can always see whether you got the results correct or incorrect, whether eventually the address that you generate is the same as this address, and so on and so forth. Okay, now let's go back to our code for a minute. Now, this code basically will generate, every time I run this code, no matter what, it will generate a new random private key. Okay, so you can see it's a different private key now. I run it again, I get a different private key, and so on. Just keeps on giving me random private keys. Each one of those private keys is a standard, and it is an acceptable private key. But because this is a video tutorial, I want to work on the same private key throughout this video tutorial. I don't want the private key to change no matter what I'm doing. I want to have a static variable. So I'm just going to comment this line out and create a new variable called private key. And in this variable, I'm going to paste the private key we just generated. This way, no matter how many times I will run this program, it will always be with the same private key. And again, this time I'm not going to do it randomly. I want to have a static private key so it will be much easier to follow my steps in this video. Okay, so now that we have a private key, we need to convert it into a public key. And the conversion into a public key is done using a function, a mathematical function, called ecdsa, or elliptic curve digital signature algorithm. Yeah, that's what it stands for. And this is quite a complex mathematical function. I'm not going to go in these tutorials on the mathematical backgrounds. Basically, I think the mathematical backgrounds are quite too complex. If you are not at least striving toward an MS in, mathematics or physics or computer science and stuff like that, I really suggest don't go down this path. If you're interested in it, just search it yourself. I'm not really going to go into mathematical function. I'm going to use an external library to do the mathematical processing for me. And I'm going to install it using pip install ecdsa. Now, as you can see, I already have it installed on my computer. I am using version 7.0.2. This is the one I am using. It says that I should upgrade, but later on, not now. I'm not going to upgrade it now. And that's it. Just install it on your computer. Let's import ecdsa. So let's go back to our browser. You can see I've already opened here the ecdsa documentation. And let's see where it is. I'm looking for sign-in key from a string. I can't seem to find it. I saw it a few minutes ago. From string. Here it is. Okay. Here we are. So basically we want to create a sign-in key, and you want to create a sign-in key from a string using a certain curve. Let's just copy this line. Or I'll just write it. Okay, so let's just create a variable. We call it sk for sign-in key. Let's get this one out of the way, this window out of the way, okay. So sk for sign-in key, and the module is ecdsa, and the function is a sign-in key. It is with capital S and capital K for sign-in key. From string, and the string is the private key, we need to decode it because it's in hexadecimal at the moment. Hexadecimal is okay for the representation in the Bitcoin protocol, but it's not the one we're going to work with. And we need to define the mathematical curves which we are going to use. And this curve going to be the ecdsa curve of SECP, this is capital letter, 256, lowercase k, and 1. I got it right, I hope? No, it's not right. What is wrong here? Let's see. Maybe I shouldn't write curve. Oh, I forgot comment. You put a comma. Yeah, no, it's okay. So basically, using this line of code, we created a sign-in key. We used the module ecdsa and the function sign-in key. We made a sign-in key from a string. This string is the private key. The private key was represented in hexadecimal, so we just decoded it back to binaries. And we defined the curve. The curve is a mathematical term. I'm not going to go into the mathematical details. As I said earlier, it's quite complex. I don't really think you should go into it unless you're like striving for PhD in mathematics or MS in computer science and engineering, stuff like that. It's quite complex mathematics. That's why I'm using this external function. But just make sure that you are using the SECP 256K1 curve. It's quite important. Here we go. Let's remove this. Now the SK, the sign-in key, will allow us to sign messages. We still need to create a verifying key. This key will be used for verification, and this verification, this is the actual public key. This is the key that we can show to other people, and they can use it in order to verify messages that we signed using our own private key. So let's create VK. VK is for verification key. And this is quite simple. You just take the sign-in key and you use the function verifying key. That's it. Yeah, no errors. That's it. And now the VK, this is basically the public key. We can give it to other people and they can use it to verify messages that we signed. But it's still not in a format that that is specified in the Bitcoin protocol, in the Bitcoin documentation. There are still a few changes we need to do on this verification key. But before we move along, I want to show you how I can use the sign key in order to take a message and sign that message. And then I can provide this message with my private key. And on the other side, the person who has both my message and my verification key, my public key, can verify that I am actually the one who signed that message. So let's do it. Let's create a simple message. We are going to call it, I don't know, hello world, of course. That's the default one, I guess. And we are going to sign that message. We can see it in the documentation page over here. Here it is. I'm going to sign this message using my SK, my sign key. I'm going to use the function sign. I'm going to sign that message, and then I will get a signature. So signature, or basically this is signed message. And this signed message, it's my sign-in key. Sign. I will insert the message. And right now, if I want, I'm going to print signed message. You see I get some sort of weird binary. I can encode this binary into hexadecimal to make it more readable. So this is my signed message over here. But it's still quite unreadable. I mean, it doesn't make much sense, of course. Let's remove it. Now I can send to another person 3 items. I can send him the verification key, the original message, this is the verification key over here, the original message, and the signed message. When I send him all of those 3 items, he can use them in order to verify that I am the one who actually signed this message, that my signature is an authentic signature, that it wasn't forged, that nobody tried to, use my signature on another piece of paper, on another message, for example, that nobody tried to change the message, and so on. So let's see how it works. So that's it, it's right over here in the documentation. You can see we have this line over here, assert. Assert basically means try to evaluate whether it's true or false. VK, this is my verification key. It's a public key. I can send it and show it to everybody. I don't care, everybody can see my public key. I just share it with everyone. This is my signature. This is my signed message, the message that I just signed. And this is the original message. Only if all of those 3 items matches together, only if I do have the right verification key, and this verification key can prove that I do have the correct message and the correct signature, only then I will receive true. Otherwise, I will just receive false. And this is basically how the Bitcoin protocol, how it proves that the man who just created a transaction or the man who just created a message is the rightful owner of the public key that are specified in this message. So let's see how it works. Got assert, verification key. We said verify, verify. Verify. Now we need to give it the signature, the signed message, and the original message itself. Hello, world. Let's see. Cool. No error means it was correct. Let's go down here. If we do try to change it a little bit, if we try to change the message, give the signature on a different message, for example, hello world. Let's say hello. We're going to see that we received an error. It basically says bad signature error because the message doesn't fit. Only if I type hello world, only then it would say, okay, you do have the verification. Sorry. Hello world, of course. Only then it will say, okay, you do have the verification key, you do have the original signed message, and you do have the original message itself, and everything matches. That's okay. You can move on with the program. You can do other stuff with it. That was just to show you how this stuff might work. When we go to transaction, this is when we're going to actually create transaction. We're going to actually sign this transaction. This is when this part will become more substantial. That was just to show you how we are going to use the public key and the private key. Again, the VK is public. I don't mind showing it to everyone. The SK, this is private. I'm just going to use it to sign documentation. I keep it to myself. I won't show it to anyone. Public, private. Let's remove this away. Get this one out. Okay, let's move along now. As I just said, the VK is the verification key. This is the public key. But again, it is not in the format that the Bitcoin protocol expects it to be. So we need to change it a little bit. Let's see over here. Not here. Here it is. Public key to addresses. Now the public key, as you can see, it says the X integer and the Y integer. Again, this is mathematical stuff. I'm not going to go into it. But basically right now we already have a 64 byte long. This is this VK over here. It's 65 byte long. And all we need to do is to insert another byte at the beginning. And this byte should be 04. So let's go back to our code. We are going to create a public key. And this public key, it's basically going to be our verification key. We are going to use the function toString, which will convert the verification key to string. Of course, it's equal. And we also need to insert right at the beginning another byte, which is 04, as we saw in the documentation over here, 04. OX04, that means we need to insert another byte, 04, plus. And because, as we saw earlier, it needs to be represented in hexadecimal, so that just encode everything into hexadecimal. Cool. And let's print it out. Print. This is my public key. Here we go. And public key. Cool. And now this number, this very, very long number over here, this is my public key. Now I want to show you something. Remember this number, 040885. You can go here to bit addresses. And we can go down here. You can see public key, 130 characters. And you see this is our public key, 040885, all the way up to 5633 in the end. Yes, 5633. You see it's very, very useful that I can check it using bit addresses. This way I know that I received the right address, the right public key. Yeah. That's it. Right now, this is my public key. This is how I'm going to transmit it on the Bitcoin network. Cool. Let's move on. We still need to convert this public key into an address. So let's see what is the next step. It's not here. It's over here. No, it's over here. Okay. So the next step, in order to convert my public key into address, will be to take the public key and use a mathematical hashing function called SHA-256, and then using another type of hashing function called RAP-EMD-160. Okay. So let's do it. Back to our code. We are going to import the hashlib module. Import hashlib module. Okay. Now, in order to use the RIPEMD160 function, I first need to define it as a new object. So I'm going to define a new RIPEMD160 object. And this object is going to be a new hashlib object. And I'm going to give it the following parameter, which is RIPEMD160. This object over here will be used in order to perform the second hashing. The SHA can still be used as before, as we did in the previous video. So now I'm just going to take this object, the RIPEMD160, and I'm going to update this object. Updating this object basically means to perform the hashing function. And I'm also going to perform the first hashing function, which is the SHA-256. So it's going to be hashlib SHA-256. I know it's a bit confusing. Why do we have to define one object and then we don't have to define an object? I don't really know why they made it this way, but this is how it's done. You can read more about it in the hashlib documentation if you want. But again, it's a bit pointless. This is just how they do it. This is how we are going to do it. So just deal with it. And then the hashing needs to be done on the public key. Now the public key is of course represented as an hexadecimal. So it needs to be decoded from hexadecimal. And as before, we need to digest the result of the SHA-256. So let's take the result of the SHA-256 and let's digest it. Digest. And that's it. Let's hope I won't get any error. Let's see. Oh, of course, I'm not decoding the entire SHA. I'm only decoding my public key. And the entire result needs to be digested. Yes, good. Now pay attention, I've only digested it once. I only digested the result of the first SHA. I need to also digest the results of the second hashing function. So let's do it here. I just want to be a bit more organized. Digest. Here we go. Cool, no errors. Okay, and that step is over. Let's see what is the next step now. The next step will be to add a network ID byte. Okay, so I'm just going to add a network ID byte, and we are going to work with the main network. Again, it is quite dangerous to work with the main network, but it is the most predictable network, so this is the one we are going to use. In order to work with the main network, we need to insert one byte, and this byte should be 0. Okay, so let's do it. I'm going to create a variable now, so it will be a bit easier to work with it. I'm going to call this variable just middleman. That's our middleman. And the first byte should be 0, plus the result of the RIP EMD 160 that is digested. Let's put it here. Cool. Let's see, no errors, good. Okay, so now that we have this middleman, let's see what is the next step. The next step is again another hashing. We need to do another double hashing over this middleman variable we just created. Okay, so let's do it. We're going to hash it twice. Just like in the previous video, we are going to let's give this variable a name so it will be easier to work with. Call it double hash. And this double hash should be hashlib SHA-256 of the middleman. We need to take the result, digest it, and then we need to take the entire result, hash it again, hashlib SHA-256, and of course we need to digest it again. No errors, good. Now you can see that this double hashing, it basically created a checksum. Remember, just like we did before? So I changed the variable name from double hash to checksum, because this is the checksum. Checksum. No, we don't need it. Checksum. And you can see that just like in the previous video, we only want the first 4 bytes of it out of it. 4 bytes. It's represented over here. Only first 4 bytes. Here we go. And you can see that we have this 25 byte long binary address. And this binary address, it might be seemed as if it's made out of 3 different sections. And I think that, yeah, technically it is made out of 3 different sections. But for us, we already have a variable called middleman. And this middleman, it is the first byte over here. We have a 1 byte. This byte is the network ID byte, which is 00. Another 20 byte from the RIP EMD and the SHA hashing. So basically those 2 parts, the 1 byte plus 20 byte, this is basically our middleman over here. Middleman. This is the This is 1 byte. This is another 20 byte. So this is the middleman. And the last 4 bytes, this is basically the first 4 bytes out of this checksum over here. 4 bytes, the first 4 bytes out of the checksum. So let's just construct it together into a binary address. We're going to call it binary address. And the binary address is the middleman. The middleman is 21 byte long. The first byte is network ID, and the second 20 bytes, this is the result of the hashing we did earlier, of this hashing in here in the middle, plus the checksum. The checksum, again, this is the first 4 bytes out of the hashing we did over here. This is the first 4 bytes. Only this time we put it at the end over here. And right now we have the binary address. Let's see, no errors. And all we need to do is to convert this binary address into a Bitcoin readable address. Now in Bitcoin they use something called base 58. Base 58 basically means that some letters and number were removed out of the alphabet. They did it to make the addresses a bit more human readable. You know, they don't have letters like a capital I, because capital I might look like 1, and they don't have letters like a lowercase l, and they don't have the number 0, so you won't get confused with O. I guess that at some point they actually believed that we are going to read and write those numbers and those addresses manually, which is quite impossible actually, but it's nice that they have at least tried to make it a bit more human-friendly. Now, in order to make these changes on the alphabet, I'm going to use a built-in library. This built-in library is called base 58. Let's see over here. So I'm just going to install it using pip install base 58. Again, I already have it installed on my machine. It says that I have a newer version available. I'm not going to upgrade at the moment. That's it. And let's import this module. Import base 58. And the final address, we are going to use the module base 58. The function b58 encode. It has this function. It will encode this message into a b58 base, which basically means it will remove some of the characters, it will replace them with others, and we are going to insert our binary address. And basically this is it. Right now, if everything is corrected, everything is done right, we should receive our Bitcoin address. So let's try to print it out, and let's hope it will work. Print. This is my Bitcoin address. I'm going to do it like this. And let's print it. And here we go. We can see that our Bitcoin address is 17x4s8j. Let's go back to bit addresses and let's see if you got it corrected. No, over here, bit addresses. And yes, 17x4s8j should end with M42G. Let's hope it will. Yeah, M42G. And this is it. And this is how you go from a private key to a public key to a Bitcoin address. And I already show you, and I've also showed you in this video what you can do with the public key and the private key, how you can sign a message and how you can verify this message, which is very useful when you are going to do a transaction. If you didn't really understood the process of signing and verifying a message, it's not that important. It's not that important at this stage. I will talk a little bit more about it in the transaction video, which will of course be the next video. That's it. I hope that you enjoyed this video and that you find it informative.